And I will be talking about my project, which is Genetic Computation Assisted Diffusion Model. This will be the agenda. We'll be going over the problem statement, the background, followed by the current work, methodology, result, and the future works. Starting with the problem statement, real-world datasets introduce sensitivity for diffusion models as they have different noise types, and which makes it challenging for diffusion model, and they require fine-tuning. Now, manual fine-tuning of diffusion model hyperparameters is labor-intensive and is prone to overfitting, which consequently impacts the model performance. To address this problem statement, I have explored evolutionary algorithm-based solution. Evolutionary algorithm or genetic algorithm are effective in exploring large parameter spaces, and they seek optimal solutions through a population-based strategy. I have investigated or explored a genetic algorithm-assisted diffusion model for the image generation task. Talking about the background, this is the general workflow for the evolutionary algorithm. Essentially, they maintain a population and calculate the fitness of all solution. Which in this case, we use the loss function to eventually calculate the fitness function. The fittest individual survives, which leads the offspring through crossover and mutation. With the crossover and mutation, the evolutionary algorithm does not get stuck into the local optimal solutions and does not also encounter problems like gradient extension and explosion. Coming to the current work, there have been numerous work which are focused on parameter-efficient transfer learning. These approaches are frequently static and involve human selection, and they may not adequately embrace the different noise characteristics in real-world datasets. Some work have focused on using different adapters and converting big diffusion models into smaller models. Recently, a couple of work have focused on evolutionary computation-assisted generative adversarial networks, and this serves as a motivation for my work of using genetic algorithms with diffusion models. Coming to the strategy, the architecture follows the evolutionary algorithm standard procedure. The population is initialized with the initial network weight. The input image is then fed to the diffusion model, and we compute the mean squared error loss between the generated image and the noisy version of the clean image, and which is later used to calculate the fitness for every solution parameter. And finally, the best solution weight is retained and is used to in the next generation cycle. The population is mutated with crossover and mutation, and the cycle goes on for the defined number of generations until we see convergence and in the fitness value of the solutions. Finally, the best solution weight is used with the model for the prediction task. Talking about the results and evaluation, this slide shows the quality of the image generated by the diffusion model, which is trained using the conventional method, and with the one which is fine-tuned with using genetic algorithm. We see better recognition of certain features in some of the images as compared to the vanilla version with the same level of training iteration. This brings us to a couple of strengths with the evolutionary assisted diffusion model. They are able to locate distinctive patterns like the yellow-orange line, as you can see in the previous slide. The quality of the image generation or the image generated and the feature recognized is superior in most cases when diffusion model is used with the genetic algorithm. This shows potential promise for integrating evolutionary algorithms with the diffusion models. And however, having said that, there are a couple of limitations that I encountered. Despite their strengths, evolutionary algorithm present challenges in terms of higher system memory and requirements, particularly when compared to the standard diffusion model. They also struggle with working with large pre-trained models and larger aperture sizes and image resolution. That leads to a requirement for redesigning the genetic algorithms to work with large models we have out there and with higher image resolution. This serves as a foundation for the future work, which involves improving the genetic algorithm to work with large models and datasets, and exploring genetic algorithms with stable diffusion models for diverse generation tasks. And I would like to thank Dr. Dana Barari for the awesome course in the semester.